Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're very pleased to have Neil Koblitz from University of Washington visiting and speaking on special versus random curves. Neil Koblitz is the founder of elliptic curve cryptography and the author of several books, including a book on cryptography called Introduction to Number Theory and Cryptography. And he has visited us several times here at Microsoft Research, but not for quite a while. So we're very pleased to have him. Thanks.
Thank you, Kristen, and thank you for the invitation. I'm very glad to be here. This talk is based on a paper, a much longer paper, written jointly with Alfred Menezes and with my wife, Ann Hibner Koblitz, that's posted on the ePrint server, if you're interested. And I want to apologize in advance for clumsiness in my use of PowerPoint. This is only the second PowerPoint talk that I've ever given. The first one was a disaster, so... Okay, so the conventional wisdom in cryptography is that you get greater security if you choose any parameters that are at your disposal as randomly as possible. So that, in particular, in elliptic and hyperelliptic curve cryptography, the safest option is to choose the defining equation to have random coefficients. Now, it doesn't mean you can't use special curves. Special choice of parameters often improve efficiency. And if you're only interested in short-term security, or if you're not particularly paranoid about security issues, that's fine. But someday that choice might be one that you regret. At least that's the conventional wisdom. Now, so for example, when I proposed hyperelliptic cryptography in the late 80s, one could justify the choice of hyperelliptic curves as opposed to elliptic curves by thinking in terms of this conventional wisdom. So the idea is that there's a new parameter, namely the genus of the curve. An elliptic curve has genus 1. We can vary g instead of fixing it to be 1. So, and I thought that the higher the genus, the more complicated an object you're working with. The Jacobian group of the hyperelliptic curve is a more complicated object than an elliptic curve. And you might just choose g randomly, like to be a random prime number. So here, in a paper I wrote a couple years later, I chose a random prime, namely 191, which has no special properties. And I gave a specific curve that was easy to compute the number of points on because I didn't have any point counting technique, so I just chose a very simple curve. And its Jacobian group has 3 times the prime number of points. I said this might be good for cryptography. At the time I was also thinking that let's take, say, g equals 191 over the field of 2 elements, which would result in a group of approximately the size you want. We could choose maybe even random coefficients, and it's just a lot better, I thought. Let's say that would give you 382 random coefficients rather than 2 random coefficients that you have with elliptic curves. Well, my fallacies at the time were, first of all, conceptual complexity is not the same thing as computational complexity, because that was the first elementary fallacy. When you read books about introductory books about algebraic geometry and curves, they talk about g as a measure of the complexity of the curve. But it turns out that even a random genus g curve over the field of 2 elements is not helped from the standpoint of security by all the hundreds of random coefficients you can have. So there were basically 2 fallacies. One thinking that having a large number of randomly chosen parameters would help security, and the other was the fallacy of thinking that a more complicated object would help. A more complex object would mean greater complexity of the computational problem. And both of these were basically rookie mistakes that I made at the time in thinking these things. In fact, thinking that the more random parameters you have to play with, the greater the security, is almost as silly a mistake as the classic beginner's mistake of thinking that if you have a very large key space, you're safe. It's on that level. Well, it's well known what happened. In 1994, Adelman, Dumaris, and Huang showed that high genus curves over small fields are insecure, and this was a big disappointment to me and a big shock at the time, although it didn't mean that hyperelliptic curves were totally useless.
If I get it right, low genus curves of these fields are insecure trivially, because there just aren't enough points.
Yes. In this, you're going to want a group of a certain size. You know, the size is essentially fixed, or the bit length of the size of the group is basically fixed. Yeah. Okay. So right now, it's known that basically the only genus that's a serious contender for being as secure as elliptic curves is genus 2. That even genus 3, asymptotically anyway, can be, the discrete log problem can be broken. Discrete log problem, of course, is the fundamental hard problem that's at the heart of all of these systems. And if you compare the discrete log problem on a genus G curve for G greater than 3 for fixed bit length of the group size, you need larger groups for the same level of security if genus is 3 or greater. It's only genus 2 that remains as a serious contender. Notice that one of my fallacies was that you can have the same word with a common real world meaning and then a special cryptography type meaning. So in that case, it was the word complexity, which means something in a conceptual sense, but it means something different in a computational sense. And the same goes for another word that I want to talk about today, which is special as opposed to random. That also has to be a word that has to be used with care. And let me give an example, a recent example that shows some of the difficulty of this word. Now, from a mathematical standpoint, for genus at least 3, the moduli space of genus G curves has dimension 3G minus 3, whereas the subspace or submanifold consisting of the hyperelliptic curves is much smaller. It has codimension G minus 2. That is, if you choose a curve randomly over the field of Q elements, it has a 1 out of Q to the G minus 2 chance of being hyperelliptic. So in terms of the dimension of the space of these curves, the hyperelliptic curves are very special subset of all curves. So conceptually, the hyperelliptic curves are special, and the non-hyperelliptic curves are the generic ones, in the sense that a random curve is almost certain to be non-hyperelliptic. Yet a few years ago, Diem and Tomei found an index calculus attack on the discrete log problem in the Jacobian group of a genus 3 non-hyperelliptic curve with running time of order q to the 1 bounded by q to the 1 plus epsilon. So now the generic discrete log algorithm, so-called square root algorithms, in this case, the group involved, if you have a genus 3 curve over the field of Q elements, the Jacobian group will have order Q cubed, and so this is like a cube root attack. Now in the case of hyperelliptic curves, the best one can do, the fastest attack on the discrete log problem, is Q to the 4/3 plus epsilon, which is slower. So in the case of the non-hyperelliptic curves, there's a cube root attack. That is, an attack whose running time is of order the cube root of the group order, whereas in the hyperelliptic case, it's a 4/9 power attack. Now, as I said, once you get up to genus 3, you can do better than the square root attack. That's why genus 3 is not fully competitive with elliptic curves. For a well-chosen elliptic curve, there's nothing better than a square root attack. In the case of a hyperelliptic genus 3 curve, there's a 4/9 power attack on the discrete log problem. And in the case of a non-hyperelliptic curve, there's a still better attack, cube root attack. So the hyperelliptic algorithm is better than the square root algorithm, but the non-hyperelliptic algorithm is still better. Oh, and I should say that there is a conceptual reason for it. What's at the heart of this discrepancy is that a non-hyperelliptic curve can be represented as a smooth curve on the smooth plane curve of degree 4, whereas a hyperelliptic curve cannot be so represented. And it was the possibility of representing a curve in that particular way that led to the Diem-Tomé algorithm. Diem was able to generalize this to a very large class, so-called sufficiently general non-hyperelliptic curves of any genus, and he found that expression 2 minus 2 divided by g minus 1 plus epsilon for non-hyperelliptic curves. This is an arbitrary genus at least 3. And this should be compared with the best general algorithm for the hyperelliptic case, which has a slower running time because you have g in the denominator rather than g minus 1. So what happened in genus 3 also occurs in higher genus as well. So what that means is that in terms of the complexity of the attack on the discrete log problem, a g-dimensional non-hyperelliptic group has the same complexity as a g minus 1 dimensional hyperelliptic group. So you have to go to one higher dimension to get the same level of complexity in your problem if you're using non-hyperelliptic curves. So with hyperelliptic curves, you can achieve the same level of security with one lower genus, meaning one lower dimension of the group, which is a big difference in its size, q to the g versus q to the g minus 1. Okay. So the conclusion is that given the present state-of-the-art algorithms, for genus at least 3, a random genus G curve is less secure than genus G hyperelliptic curve. So, okay, so now I want to go to another issue or another part of my talk about the whole question of special versus random. And this is sort of interesting from, I guess, a sociological standpoint, because one sees on this issue of preferring special versus random curves, you see a sort of national division here between NSA and the German equivalent BSI. Now, NSA has a long history of supporting the use of special curves in elliptic curve cryptography. In fact, the very first public presentation at a crypto conference by an NSA person was Jerry Salinas' paper at Crypto 97 on anomalous binary curves, which have their equation defined over the field of 2 elements. They're basically the ordinary curves over the field of 2 elements. And his paper was devoted to very efficient computations on those curves that improve the efficiency of crypto systems based on those curves. In addition, NIST, which is essentially NSA, has implicitly endorsed pairing-based cryptography, and they organized a workshop on it in June. At that workshop, a company, Voltage, presented a choice of curve for pairing-based cryptography, namely the supersingular curve y squared equals x cubed plus b over a prime field, where 12 divides p plus 1, which among other things means that it's supersingular. And this is a very, very special curve. It has all sorts of special properties. So that's another example. It's not exactly NSA pushing this, but it's certainly NIST has been very cooperative with pairing-based cryptography. Meanwhile, yeah?
Do you happen to know if Voltage has any patents on speeding up that particular curve?
They might. I don't know what the patent situation is, though. Now there's a European consortium called Brainpool that's led essentially by BSI that has made some very different recommendations that I think provide an amusing contrast with the role that NSA and NIST have been playing. First of all, according to their draft recommendations, when you have an elliptic curve over a finite field can be lifted to a curve over a complex multiplication field. And they insist that that number field must have degree greater than 10 million. So if it lifts to a field like voltage's curve lifts to a curve over the rational numbers, which has degree 1. So, so it very much violates this, to say the least. That also precludes the anomalous binary curves, which have complex multiplication by a class number 1 number ring.
Did they say why they want polynomial?
Why? Well, presumably to prevent the possibility that someday someone will find a way to use the theory of global elliptic curves over those number fields. They want the number field to be big enough so that computations are not feasible there in case someone finds a way to use computations there in some sort of attack. So it's based on speculation related to possibilities for future attacks. Secondly, they require that the embedding degree, by the embedding degree in an elliptic curve system, it means the smallest degree of an extension of the finite field into which the elliptic curve group can be embedded. So you can embed an elliptic curve group into the multiplicative group of a finite field, but you have to go to a field extension to do that. And in a randomly chosen situation, if your parameters are random, that extension degree will be astronomically big. And that's what they insist on. In fact, they insist on that the embedding degree, that's the degree of the field extension, should be greater than q minus 1 over 100. Pardon?
Is this motivated by a theorem with Balasubramanian?
Their requirement, their reason for doing this? Well, certainly avoiding very small embedding degree has a reason connected with the discrete log problem in the finite field. Why it should be that big, I mean, you really have to ask them, you know. So in particular, this immediately precludes all pairing-based cryptography. Now, they really want to err on the side of caution because, for example, they're saying that if you use an elliptic curve that embeds in a finite field extension of q minus 1 over 1,000, that's too risky. So that would mean if k has so that would mean q is presumably has about 160 bits. So if k has 150 bits, that's too risky. Now, yeah.
If I remember rightly, the NSA and NIST say 160 bits should be pensioned off by 2010. They have key lengths, and in 2 years' time, 160 bit will be more or less excommunicated.
Okay. This is just just to give an idea. But let's say that k has only 160. The field size has 160 bits. In that case, we're talking about k of 150 bits, and you certainly wouldn't have it any less than that. So k, this excluded k by Brainpool, would have at least 150 bits. Now, the fastest algorithm for the discrete log problem in that field has running time. This number, the running time is about 10 to the 400 trillion operations. But still, that's not safe enough, according to Brainpool. Well, in practice, what they're really doing is they're insisting on random curves.
So do you think they know any better algorithms for curves with CM by small discriminant field?
I don't think so, but I'm not privy to what they might know, but I don't think so. So in practice, what they're really doing is saying we have to use random curves. So they won't allow you to use the CM method, anomalous binary curves, supersingular curves, no pairing-based cryptography. Now that's an incredible contrast, between the two. So, and at least I found this surprising when I realized how extreme this was. Now, one theory, some might be tempted to talk about German versus American national traits. For example, in Germany, my friend Johannes Buchmann, who I was visiting many years ago in Germany, told me the story that in Germany, there's a law saying that motorists must carry some rubber gloves in their car. And I couldn't figure out why. He explained why they have this law. It's because there's a Good Samaritan law in Germany, which means that if you see an accident, you're required to stop and help the injured parties. But there's always a chance that someone who's bleeding might be HIV positive. And in that case, you still have to be a Good Samaritan, but you're required to have these rubber gloves that you can use to handle this. And this, to me, sort of like epitomized a very cautious attitude toward life. To have this requirement. Whereas in contrast, the American stereotype is that Americans are very happy to indulge in high stakes, very risky gambling. So that's a tempting explanation, but I think it's a bogus one. It's up in the air why it is that Germany went in one direction and NSA in another. And as far as in our paper, we're completely agnostic on the question of who's right about this. We're not claiming that NSA is being reckless and risky or NIST or voltage, and we're not claiming that Brainpool is being ridiculously overcautious. An argument can be made either way. But now the irony of this is that it's not really a simple issue. Do you want to be extra cautious, or do you want to be a little bit reckless, or what some people might consider to be reckless, what Brainpool would consider to be reckless? It's not really a clear-cut issue, because one can imagine scenarios where Brainpool's approach might not be the safer one, even though they're insisting on random curves. So there are various scenarios in which someone, and I'll call her Alice, who chooses ECC with a special curve might end up better off than someone else, who I'll call Bob, who chooses a random curve. So these scenarios are suggested by recent work on isogenies. So let me just quickly summarize that. But there's some people. Well, Venki, I know, is an expert on this more than I am, so I probably, and Kristen's done work on this too, so I shouldn't be the one talking about isogenies. But I'll quickly go over what the basics of what an isogeny is between two curves. So we have two elliptic curves defined over the field of Q elements. An isogeny is simply a non-constant rational map defined over FQ. That is, an isogeny defined over FQ is a non-constant rational map defined over FQ that takes the point at infinity to the point at infinity. Its degree is a rational map, which also, in the case we'll be considering, is the order of the kernel of the isogeny. An isogeny, there's a dual isogeny going the other way, and so there's an equivalence relation between elliptic curves of being isogenous. So this is a larger class than isomorphism. Then there's a basic theorem by Tate related to curves over a finite field, that they're isogynous over the finite field if and only if they have the same number of points over that finite field. Now, from a computational standpoint, it turns out that low-degree isogenies are easy to construct, but high-degree isogenies are usually not, especially if you don't have an explicit form of the isogynous curve. That is, if you're just given a curve and you want to construct an isogeny of some large prime degree, that's a very hard computational problem. Now, one also has to talk about endomorphisms here. So if we have an elliptic curve over the field of Q elements, the trace is the difference between Q plus 1 and the number of points. An endomorphism is an isogeny from the curve to itself that's defined over the algebraic closure. In the case we'll be considering, the non-supersingular curves, or ordinary curves E, which means that T is prime to the characteristic of the field. In that case, all endomorphisms defined over the algebraic closure are actually defined over the field of definition. And that's the case we'll be considering. So in the ordinary case, the case of ordinary elliptic curves, which is the usual case, the endomorphisms are all defined over the field of definition itself. Now, the endomorphisms form a ring that contains the subring of the obvious endomorphisms of scalar multiplication. Now, the delta, the discriminant of a curve is the square of the trace minus 4q, which is a negative number. And the CM field is the quadratic imaginary field generated by the square root of the discriminant. Now, that discriminant, if we write it in the form, D stands for the discriminant of the field. So D is a fundamental discriminant, the discriminant of a quadratic imaginary field. Delta, in general, is equal to the discriminant of the field multiplied by some square. And that square plays a crucial role in classifying the possible endomorphisms that the possible endomorphism rings that E could have. Well, it turns out that the endomorphism ring of E is an order of the ring of integers of that quadratic imaginary field. So this is all part of the sort of basic theory of complex multiplication. But it's not necessarily the full ring of integers. In some cases it is, in many cases it is, but in general it will be an order of the ring of integers of this quadratic imaginary field of a certain index C, which is called the conductor of the endomorphism ring, not to be confused with other meanings of the word conductor. So the conductor of the endomorphism ring of an elliptic curve tells you something about, tells you its index in the maximal possible, the largest possible endomorphism ring. So if you take all elliptic curves that are isogenous to a given elliptic curve, they can be partitioned according to their endomorphism ring. Namely, the endomorphism rings are determined by the conductor C, which are in one-to-one correspondence with the divisors of that factor that's being squared in the determinant. So these are basically all of the facts that we need, and I went through them quickly because it's part of the basic theory of complex multiplication and endomorphisms, and it would take a lot of time to go into any more detail on where all this comes from. Okay, now we ask how many isomorphism classes of elliptic curves are in a given endomorphism class. The answer is that it's the class number of the order, which is related to the class number of the field. It's essentially proportional to the conductor. That is, if in the case of conductor 1, it's the class number of the field, but if the conductor is larger, there's a larger number of isomorphism classes with the endomorphism ring. In a sense, the smaller the endomorphism ring, meaning the larger C is, the more curves there are, the more different isomorphism classes there are with that particular endomorphism ring. So that's basically what we need to know. So for example, if the discriminant is square free, then all of the curves in an isogeny class, and I should have said before that in fact the number of isomorphism classes in the isogeny class of an elliptic curve is of order of the square root of q. Remember, the isogeny classes correspond to the number of points on the curve, and the number of points on the curve fall in the Hasse interval, of which there are roughly 4 the square root of q possibilities. So there are roughly 4 the square root of q possible isogeny classes, and there are of order q elliptic curves, and so there are roughly the square root of q curves in each isogeny class. Now, if delta is square free, then they all have the same endomorphism ring of conductor 1. There's no C0 is just 1. So that's the simplest case. They're all in the same class. If another special case, if C0 is a large prime, then there are two endomorphism classes. There's the isogeny class consisting of a small number of curves whose endomorphism ring is the full ring of integers, namely the class number of the quadratic imaginary extension. That's how many, which will be a quite small number, probably. And the remaining curves, the vast majority of them, which will have endomorphism ring of conductor C0. Okay. Now, concerning the isogenies, let L denote a prime. Now, if there's a degree L isogeny between two curves, then either the two curves have the same endomorphism ring, or else the conductors differ by, in one direction or the other, by a factor of L. So, if we have two endomorphism classes, by the conductor gap, we mean the largest prime that divides one conductor and not the other. And that determines how easy it is to go from one class to another using isogenies. So what we're going to be talking about is going from one endomorphism class to another one using isogenies. And in order to change the endomorphism class, we have to have the gap between the conductors has to be the prime degree of the isogeny. Now, if there's a large conductor gap between two endomorphism classes, that is, there's a large prime that divides one conductor, the conductor of one endomorphism class, and not the conductor of another endomorphism class, then one cannot go from a curve in one class to a curve in the other by a string of low-degree isogenies. So remember, I said that in constructing isogenies, the basic fact is if you're given a curve and you want to construct a degree L isogeny where L is a prime, and that's all you're given, and you just got to construct this isogeny. If L is small, you can do it. If L is extremely large, you can't. And so if there's a large prime that divides one endomorphism class's conductor and not the other one, then in practice you can't go using isogenies from one endomorphism class to another. And conversely, if there is no large gap, then by a result of people who were here at the time, Zhao, Miller, and Benke, within an endomorphism class or among several classes, but with small conductor gaps, one can travel randomly and uniformly through the set of curves by just a string of low-degree isogenies. Now, the thing about isogenies, they allow one to transport the discrete log problem from one curve to another. So the discrete log problem is random self-reducible within a set of endomorphism classes with small conductor gaps. So what that means, well, first let me give the definition. By the L conductor gap class of E is the set of all endomorphism classes in the isogeny class of E that have small conductor gaps smaller than L. So what this means basically is that if you have, if you were to find a faster algorithm, let's say you found an algorithm that solved the discrete log problem in time t1 in a certain proportion of all elliptic curves. That there's some criterion that if an elliptic curve happened to satisfy, you could apply this new algorithm. And so there's a certain proportion of weak curves. And let's suppose that the property of being a weak curve is independent of the isogeny and endomorphism class. Then if you had an L conductor gap class, so you could travel freely around that class, then you could solve the discrete log problem on any curve in the class in time t1 plus t2 over epsilon, where t2 is the amount of time it takes you to construct a low-degree isogeny. So low degree means degree less than L. That you can, using degree less than L isogenies, you can jump around randomly and uniformly in this class. And epsilon, of course, is the proportion of weak curves. So it takes you time T2 divided by epsilon to find a weak curve, and then T1 to solve the problem once you get there. And this, of course, only works if the L conductor gap class contains more than 1 over epsilon curves, so that you have a good chance of finding a weak curve. So the whole point of this is that it's the possibility of random walks, random sort of strings of low-degree isogenies through a conductor gap class that under certain circumstances might make a random curve less secure than a special curve. So that's what I want to give some example of. Now notice, it's important to note that for a random curve, you'd expect that all isogenous curves are in the same conductor gap class, because delta has negligible probability of being divisible by the square of a large prime. So there just aren't going to be any large prime around that could divide the conductor of the endomorphism ring. So we'll look at some hypothetical scenarios. And all of this is hypothetical. And we're not talking about algorithms that, we're not talking about things that are occurring in the real world at present with random curves. Okay, so here's, I'll have time for a couple examples. Müller in '98 suggested some curves for elliptic curve cryptography that generalized slightly more general cases besides the anomalous binary curves that are defined over the field of 2 elements. He suggested some curves defined over very small degree extensions of F2. So here's an example, one of his examples. Let's let Q be 2 to the 177th power. So this is 2 to a composite degree. And let gamma, that's supposed to be a gamma, but unfortunately PowerPoint has terrible gammas, so it looks like a Y, but it's not, that's not Y, that's gamma. So let Y be a generator of the degree 3 extension of F2, satisfying gamma cubed equals gamma squared plus 1. And let E be the following elliptic curve. This is one of Müller's elliptic curves, very similar to the anomalous binary curves, but with defined over F8. Its group order is, over that particular field extension, is, so this is a prime degree extension of F8. It's a degree 59 extension of F8. And it turns out that its group order is 6 times a prime of suitable size for elliptic curve cryptography, and that was one of a handful of examples he suggested. Okay, now suppose that Alice, remember Alice is the one who's using a special curve, and she read Müller's paper and followed his suggestion and chose this E. Now she figures that solving the discrete log problem by the Pollard-Rowe method, by the square root of attack, will take roughly 2 to the 84 operations. Now there's a slight speed up whenever you have a curve defined over a smaller field and then you work with it over an extension. There's a speed up which is really quite small but still has to be taken into account of the square root of the extension degree because of ways you can group together points that are in the same conjugacy class under the Frobenius map of the extension of finite fields. So you can sort of group together points in sets of 59 points and apply Pollard-Rowe to those. Instead of to the set of points, you can apply to the set of conjugacy classes and get this little speed up. That's about speeds that reduces her security by 3 bits. So that's why she has 84 bits rather than 80. Okay. Yeah. Normally she would have. Okay, so it's a 175-bit prime, so she would normally have 87 bits, but it's reduced to 84 bits because of the speed up. Okay. Now Bob thinks that Alice is foolish, first of all, for having chosen a curve with very special properties that not only allow for this one speed up that we know about, but who knows what else could result from choosing a special curve. So it could leave her vulnerable to other attacks. So Bob figures that he'll say, fine, let's use if you want to work over the field of 177 elements, let's do that. He chooses a random curve over the same field with group order 2 always divides the group order if it's an ordinary curve. So, but you could get twice 176-bit prime working over that field with random coefficients. Then he'll get 88 bits of security rather than 84. And he'll also be less vulnerable to special attacks. So that's what he figures. Okay? So here's Bob lecturing Alice, and with condescension oozing from his voice, that she was really quite foolish to choose this very special curve. Well, he'll get more security choosing a random curve, even using the field she wants to use. And until recently, Bob's reasoning would have appeared to be correct. That is, that you'd be better off from a security standpoint using random coefficients over this field. But some work in 2006 by Alfred Menezes and Edwin Teskey on Bay descent shows that Bob might not have nearly the security level that he thinks he has. Namely, they found that a certain proportion of all elliptic curves over this particular field, the field of 177 elements, the same field that was in Mueller's paper, that a certain proportion of all elliptic curves with group order congruent to 2 mod 8, which is half of them if you choose randomly, are weak in the sense that the discrete log problem can be transported to the Jacobian of a genus 3 hyperelliptic curve over the field of 2 to the 59th element. So in Bay descent, you take a curve, an elliptic curve defined over a composite degree extension of F2, and you transport the discrete log problem to a hyperelliptic curve over a smaller field. And if you're lucky, the genus of the hyperelliptic curve will be equal. You'll get a group of the same size. You might not, but in these cases, you get a genus 3 curve over the field of 2 to the 59 element whose group order is also 2 to the 3 times 59. And there, as we saw, you have a 4/3 power, q to the 4/3 algorithm, which is about 2 to the 79th. Is how long it takes to solve the discrete log problem on that curve. And now this weak property is likely to be independent of isogeny class. Now in Bob's case, the discriminant of his curve is almost certainly not divisible by the square of a large prime, and so it'll be feasible to use isogenies to transport his discrete log problem along a random walk through the isogeny class. Now each isogeny in this case, given the current state of these algorithms, take about 2 to the 17 to construct. So in this case, epsilon is 2 to the negative 58, so it'll take just time about 2 to the 75th to transport Bob's discrete log problem to a weak curve. If his group order is congruent to 2 mod 8, their results apply only in that case. So maybe Bob's lucky. Was lucky. Of course, Bob did this before he knew about the result, so he had no way of knowing that he should avoid group orders congruent to 2 mod 8. So if he was lucky, his group order is congruent to 6 mod 8, but there's a 50% chance that his group order is congruent to 2 mod 8, in which case, in time of order 2 to the 75th, his discrete log problem can be transported to a weak curve so that he has actually 79 bits of security, not the 88 bits that he thought, and not even 84 bits as Alice has. Okay? So basically, because of this difference between genus 3 and genus 1, where in genus 3 you have a faster than square root algorithm, the 4/3 power is not that much faster than the 3/2 power of q, which is what a square root algorithm would give you, but it's enough to make a difference of in this case, 9 bits of security, and put him in a worse case than Alice. And of course, Alice also has greater efficiency with her special curve. So she sort of gets the last laugh on that. Now, even if Menezes, it turns out that Alice's group has group order congruent to 6 mod 8, but let's just say, for the sake of argument, that the Menezes-Teskey result didn't have that condition. Nevertheless, she'd still be safe because she was working with a special curve. That's because her curve's endomorphism ring has conductor 1 and lies in a conductor gap class. Now, 2 to the 66, if you choose L, that capital L, to be 2 to the 66. That's far above the range where you can construct isogenies. For a prime greater than 2 to the 66, you cannot construct an L-isogeny. Now, in this case, for her discriminant does have a very large square factor, of course, as special curves always will. And this square factor has a large prime and then an intermediate size prime. And so using isogenies, you can go from her curve, which has conductor 1, to curves that have conductor 11,681. That's feasible. It's somewhat time consuming, but it's certainly feasible to go to go outside her very small her very small endomorphism class to the endomorphism class with conductor 11,681. You can do that, but the total number of curves both in her endomorphism class and in the endomorphism class of conductor, her endomorphism class is conductor 1, and the larger endomorphism class of conductor 11,681, the total number of curves is approximately 2 to the 16th. So there's negligible probability that any one of those curves that you can get to using isogenies from her curve will be susceptible to the Menezes-Teskey version of Weil descent. So the so-called weak curves, remember they're roughly 2 to the negative 58 of all curves are weak in this setting. And because of the particular nature of her special curve and the factorization of its discriminant, there's no way of using isogenies to get from her curve to 2 to the 58 curves. So it's highly unlikely that her discrete log problem can be transported to a weak one by an isogeny walk. So what saves Alice is precisely the very special nature of her curve, the fact that it has the endomorphism ring has conductor 1. Okay, so that's an example with a composite degree extension field where these results using Weil descent apply. Now I'll be more hypothetical and imagine algorithms that don't at present exist, which Brainpool has done, so I figure they've opened the way to making maybe some outrageous speculations, so I'll do that too. Now, in the next example, we'll take a prime degree extension of the field of two elements. And in fact, in almost all practical implementations of elliptic curve cryptography, it's prime degree extension fields that are used in the characteristic 2 case. So this is more realistic in practical terms in that sense. Now let's suppose, and here's where I'm being very speculative, that some version of Weil descent or another approach someday leads to a faster than square root attack on a small but non-negligible proportion of curves defined over this prime degree extension of F2. Now right now, any of the really good Weil descent methods require a composite degree extension of F2, but it's conceivable that that could change, or that some totally different attack would apply to prime degree field extensions of F2. So let's just suppose that that happens. And let's look at the digital signature standard recommendations for 5 elliptic curves. In 2000, NIST recommended 5 specific elliptic curves over prime fields and 10 over binary fields. And they had 5 different binary fields at different security levels. And for each one, they suggested 1 random curve and 1 anomalous binary curve. Now, the largest case for greatest security is the degree 571 extension of F2, which should provide plenty of security to protect a high security AES private key. So that was the motivation for going up to that high of a degree. Now, the conventional wisdom, in line with what I was on the early slide, is that if there is any difference in security level between the two curves that are recommended for that field, the random one and the anomalous binary one, the random one, R571, is the safer choice than K571 binary curve they recommend. However, that's the conventional wisdom. Let's suppose that a proportion epsilon of all curves over this field could be attacked by this hypothetical algorithm. And let's also suppose that the weak property of being susceptible to this new algorithm is independent of isogeny and endomorphism class. Now the curve R571 has square-free discriminant, as random curves often do. And so the isogeny walks can fan out from that curve throughout the isogeny class, which consists of 2 to the 285 curves approximately. So after approximately 1 over epsilon isogenies, whatever epsilon is, the DLP, the discrete log problem, can be transported to a weak curve. But in contrast, the anomalous binary curve has discriminant. The square-free part is just -7 because it's an anomalous binary curve, which always has the discriminant for an anomalous binary curve, whatever the extension field is, always has the form -7 times the square. And in this particular case, the number squared happens to be the product of a fairly small prime and an extremely large prime. What this means, the endomorphism ring of the actual anomalous binary curve is always has conductor 1. Because it has this very large ring of endomorphism. That's in fact why it's efficient, why it was possible for Jerry Salinas to develop these really nice algorithms for point multiples. Is because you have this tremendous ring of endomorphisms to work with. So you have the full ring of integers of q root -7 endomorphisms. So it's conductor 1. And so if you take the 2 to the 262 conductor gap class of this curve, there are only about 2 to the 22 curves. That is, there's the one curve K571 itself, and then there are also about 2 to the 22 curves that have whose endomorphism ring has conductor equal to this 22-bit prime factor in C0. So if epsilon is much less than 2 to the -22, less than 1 out of 4 million probability that the special attack will work, then the discrete log problem probably cannot be transported to a weak curve by isogenies because there just aren't enough curves in its conductor gap class to move around to. And under these hypothetical assumptions, that special curve is likely to be safer than the random curve. So that's that's another example, again, hypothetical example, where the random curve could be more dangerous. And finally, a final sort of setup. Let me just suppose that we're worried about a new approach to the discrete log problem might turn out to give a faster than square root attack for a certain proportion, again a small but non-negligible proportion of curves defined over a large prime field. In that case, if we're thinking about that, we might want to choose our elliptic curve to be in a very small L conductor gap class where L is large, so that an attacker could not use isogenies to transport the problem to the discrete log problem to a weak curve. In that case, it's a very, very easy construction, which is sort of fun to ask questions about. I mean, some nice number theory question you can ask about this. Just choose B to be a random prime of whatever order you need for security. A random even number, which has a couple conditions. You want a squared plus b squared to be prime, and you want either one of those two to be prime, either p plus 1 over 2 minus a or plus a to be prime. In that case, the curve with this very special equation, y squared equals x cubed minus alpha x, has two endpoints, where alpha is a quadratic non-residue in the prime field, and the quartic residue symbol of alpha depends on the sign that we chose when we defined n. And the trace then is plus or minus 2a, and the discriminant is easily computed to be minus 4b squared, and by construction b is a prime. which is why we did that, why we chose B to be a prime. Then this particular curve up there has conductor 1. It's easy to see that it has complex multiplication by I, so it has complex multiplication by the full ring of integers. That is conductor 1. And it's the only isomorphism class in its B conductor gap class. So it can't be moved anywhere using isogenies, because you're never going to be able to construct a degree B isogeny. So all other isogenous curves have an endomorphism ring of conductor B, and for any reasonable k, it's not feasible to transport the discrete log problem from E to any other isomorphism class, any isogenous isomorphism class. Now this curve is totally against the advice of brain pool. It's very concrete, very, very special curve with no randomness in it, or hardly, very little randomness in the equation. And it completely goes against the advice of brain pool. Now, whether it's reckless to do this or wise to do that, it's just a judgment call. And we're not saying that people should use that curve. It's just if one's worried about the possibility speculatively of these sort of algorithms that might apply to only epsilon of curves, then it might be reasonable. So the conclusion is not that we should prefer special curves over random ones. I'm not making an argument that, it's bad to use random curves. And I'm not saying that brain pool is wrong. We're sort of agnostic on that question. Our only real point is that we don't really know, and that some humility in dealing with these issues is called for. And I think one of the purposes of a lot of the joint work that I've done with Alfred Menezes in recent years, especially our papers on provable security, is that there's a little bit of an excessive tendency in the cryptography world to convey to the outside world an impression of self-confidence and mathematical certainty about our recommendations, when there is some reason to wonder whether this self-confidence is justified. So a lot of sort of the flavor of what we've tried to do with various papers, including this one, is to call for some humility about expressing mathematical certainty about recommendations. So finally, I want to put this in a sort of sociological context by talking about narrative inversion, which is a term that applies when the farther the story that one tells and the language that one uses are from reality, the more fervently this narrative is repeated, and the more adamantly people insist that it's true. So some examples of narrative inversion is when a U.S. says that it's defending freedom, when macho guys use bravado to hide their insecurities. So here's some example of narrative inversion. And football, you see some examples of narrative inversion there. But in the world of cryptography, another example from outside cryptography is that very often people who work on social questions like to use the word science all the time when they talk about social science, political science. In a sense, I think the reason why they use the word science, usually if someone really is doing science, they don't go around saying, oh, look at me, I'm doing science. When someone's constantly using the word science in reference to their work, there's a good chance it's a case of narrative inversion. Similarly, in cryptography, when crypto researchers claim that their systems are provably secure, and that the rigorous methodology of provable security, and this is from a new book by Katz and Lindell's new textbook, has transformed cryptography from an art to a science. Again, using the word science and expressing this mathematical certainty, something's provably secure. You have people reacting very strongly to here's Jonathan Katz. I mentioned in my abstract that I guess in my bio that I've been making a lot of enemies recently as a result of my Notices article. And here's an example of someone getting extremely upset at discussion of some of the doubts that arise in the cryptographic world. And this is what he accused me of name-calling, sheer elitism, snobbery at its purest. And he went on to say in his, this is all from his letter to notices, AMS notices, that despite my criticisms of a lot of what goes on in provable security, so-called provable security, the definitions, proofs, and formal reasoning have helped cryptography progress from an art to a science. And this constant harping on how cryptography, thanks to the methodology of provable security, has gone from an art to a science reminds me of a line from Shakespeare about protesting too much. And that's really what narrative inversion's about. And I think a lot of what goes on when attached too much confidence to conventional wisdom and to certain assumptions does veer off in the direction of narrative inversion sometimes. So anyway, that's what I want to say about this, and I welcome questions or comments or disagreements. Yeah.
This is the first I hear of BSI. Is it also a two-headed animal like the NSA, which snoops on foreigners and tries to make sure foreigners don't snoop in the US?
I don't know. I'm not familiar with BSI's different with other differences with NSA other than the one that I talked about.
Yes.
Yeah.
So do you not think that it's not that they're saying BSI or NSA saying that their approach is more secure, but that they actually might just know a secret to the other one? Which is like the method NSA says is the best. It's because the way BSI does it, NSA knows of a weakness they don't want to tell us about. Like last time we heard the NSA do this, they said use this special box or S key for.
So you're saying that NSA is proposed? Say this again.
The reason that they don't like BSI's method is because they know an attack for the way that BSI says is the safe one.
Something of the form that I was talking about, something like an attack that works in a certain proportion, and they know they can get at a random curve, but they can't get at a special curve. I would tend to really doubt that. I mean, theoretically, it could be. I think there's a little bit of a tendency we have to overestimate what NSA knows and what other secret agencies know. It's now, I believe it's certain, for example, that none of those agencies had thought of elliptic curve cryptography. It's known that in Britain they did think about something similar to RSA a few years before RSA did, but they messed it up. I mean, they didn't appreciate its importance. They put it on the back burner. They sort of didn't do it right. It was only in the academic world where Diffie, Hellman, and the RSA people and others understood how to do it right. So I think sometimes we tend to, because they're secret, we tend to overestimate what's there. And I'm not saying they don't do good work, but I'm just a little skeptical that they would have some brilliant attack on random curves that has eluded everybody who works in the open. That's just my personal view. And I think the history, the things that have become known about what these agencies do don't suggest that they're light years ahead of everyone else. But that would just be my opinion. It's conceivable, of course, that they know this. Some people would turn it around and say, well, maybe, on the contrary, they know how to break anomalous binary curves, and that's why they're recommending them, so that people will use them and then they can break them. So people can imagine various scenarios, that they're either recommending something because they know that the alternative is weak, or that they're recommending something because they know the alternative is strong. So my guess is neither.
The question about the BSI number of 10 million that you have. You know how the numbers behaves over time? Once looked at this in the mid-1990s, it was degree 100. And 2 years later, it was 400.
Of what number?
That number 10 million that you had for the degree of the of the class field in this case. It was degree 100 in 95. 499. Have a look at it since. Now it's all of a sudden 10 million. You know anything?
I don't know. I don't know why degree more than one is necessary. So I'm still stuck at 1. So so between 400 and 10 million, I can't really see any basis even for going above 1.
So just on the nomenclature, when we say special versus random, so it seems like this is also an example of kind of what you were saying in the beginning, where words can end up being taken to mean something that they don't actually mean. So somehow these words special occur getting assigned to, something that has, like for example, CM by a field of very small discriminant. So if then you take that to mean special, which of course no one in the non-mathematical world thinks that that's what the word special means, but in a lot of these cases that is actually what's happening. It just happens to be a field of small discriminant. And then you take and you look at it from a different angle where you actually have this issue of the large, conductor gap to take into account. Well, if you just used the English language and used the word special to apply to the ones that were on the wrong side of the large conductor gap problem, then you could flip the whole thing around. And so I was wondering really how intrinsic the words special and random are in your title. It seems like.
Well, the story about hyperelliptic, non-hyperelliptic curves supports what you say, that it's tricky sometimes to say which is special and which isn't special. Although I think usually people mean if something's chosen randomly in a certain set, and you have negligible probability of getting something with a certain property, then that's distinguished from particularly looking for something with that particular property. So I guess in some sense that's a well-defined distinction. But in the case of hyperelliptic, non-hyperelliptic curves, I don't think anybody would use the word special for non-hyperelliptic curves. I don't think anybody would call hyperelliptic curves the generic case and non-hyperelliptic curves special. But if you look at Diem's algorithm, it's almost as if it was that way. So his algorithm could be viewed as showing a weakness in a special, in a generic curve as opposed to a special curve. But as you say, we could just sort of reverse the meaning of the word. We could just reverse the usage of the word special, and that would take care of it. But these words do have reasonable accepted meanings, but it's just that the reasonable accepted meaning, at least if we use it to be consistent with real world uses of the word, with dictionary uses of the word, there might be some surprising consequences where something special turns out to be safer than something general, or something simple turns out to have more complexity in its discrete log problem than something complicated. So we get a sort of discrepancy between the commonly accepted connotation of a word and what actually happens in cryptography. And I think that's also true, we were talking about this earlier, about the word term provable security, that the terms carry a lot of baggage, a lot of connotation that comes from their outside world usage. And sometimes when we use words in cryptography that have this baggage attached to them, people can get confused and can assume that certain things are going to happen, and the reverse might happen. People can expect a certain level of certainty when they hear the word provable. Well, as I think it was Lars Knudsen once said, if something is provably secure, then it probably isn't. Sometimes that can happen, that a word seems to be implying something, but what actually might happen is the reverse. But whether this can be fixed by just changing the usage of the words, or just maybe avoiding loaded words entirely, or just avoiding putting too much confidence in conventional wisdom, and sort of being a little bit sensitive to the tendency to allow the terminology to take us farther in interpreting something than we have any right to go with it. That sometimes the terminology develops its own momentum, and people conclude certain things. They conclude they can have a lot of confidence because something's provably secure, or they conclude that they should make a random choice because it sounds right, or the terminology suggests that. So I think we have to be cautious whether we can accomplish anything by changing our word usage, maybe sometimes we can do that too.
Other questions?
Yes?
First attack you showed against the random curve, you showed you doing a 9-bit reduction, and then you went through some hypothetical attacks. Do you have any estimates? You know, obviously it's all hypothetical, of how many bit reductions that would result in?
Well, there's no way of knowing because it is hypothetical. A weak curve, by the term weak curve, I meant a curve for which a quicker algorithm's known. Now, in this case, we were talking about, when we talk about genus 3 curves, these are still exponential time algorithms. They're an improvement over square root attacks, but not a super dramatic improvement. So that's why it was just 9 bits improvement. Now, clearly, if we had, but nothing like this is remotely known, but if we had, say, a polynomial time attack on the discrete log problem for a certain proportion of the curves, then conceivably the time that it would take to solve the problem would be just dominated by the isogeny walk. In other words, once you found a weak curve, you'd be home free because you'd have a very quick algorithm. So you could imagine a situation where the only real obstacle to solving the discrete log problem on a random curve was implementing the isogeny walk to find a weak curve. So depending on what happens, since it's all hypothetical, there's no way of knowing, a weak curve might mean very weak or just a little bit weak, and a weak curve might occur with very little frequency, in which case it could take a long, long time to find one, but maybe once you found one, the actual algorithm would be very quick. Or as in this case, where we actually do have an algorithm using Weil descent, it is you only get 9 bits. So it really depends, and since this is hypothetical, no way to know.
Okay, well, let's thank Neil again for his very good.
Thank you.